Hi guys, today we're doing an experiment on geometrical optics. So today we're gonna use a simulator. We're gonna move objects to different positions and observe their image. So here I have we're gonna test 5 different conditions and observe how the image changes. So this is the formula of our focal length. Okay, let's start. In our first case, we have to put the distance between the object more than 2 focal points. Here, let's take a ruler and see that the distance between the image and focal point is 80 centimeters. So in the first case, it should be more than 2. So 80 multiplied by 2 is going to be 160. Here it's gonna be approximately right here. So it should be more. It's actually in the right place. So here we can see the result that the image is real, it's inverted, and it's smaller. The next one, it should be exactly 2 focal points. So it's going to be like this, and we can see that the image is real, it's inverted, and the same size as the object. So now let's put it between focal point and second focal point. So it's going to be, let's put it in the middle, so it's approximately like this. Here we can see that the image is still real. It's inverted and it's large, so it's magnified. Now let's have the object be at the focal point exactly. So we can see that no image is formed on the screen and the rays are parallel. See? And image appears as infinity. We can't see it on the screen. So right now we are going to put the object closer than the focal point. And we can see that it's virtual, it's upright, and it's magnified. Okay, so we tested 5 different ways, different positions of the object, and we can do a conclusion that how image position changes, it changes as the object moves. So we saw when image is real and when it's virtual, and we compared the focal length and the actual length. That's it, thank you. Our experiment number 2 is going to be about density. So first of all, we're going to have an experiment where we have 4 blocks, and we're going to check how density affects if they sink or float. So first of all, here's the main formula. We know that ρ is equal to m divided by v. M is our mass, v is our volume, and ρ is our density. So we're gonna have different cases. Case number 1, where the objects with the same mass. So same mass but different volume. So let's see. As you can see, some objects sink and some blocks float. So when mass is the same, density depends only on volume. Here we can see that the smaller volume, high density, equals sinking, and large volume equals low density, so the object floats. Let's see case number 2, where we have the same volume. Okay, so our volume is equal to 5 liters. Okay, so let's get the blocks. here, as we can see, also some of the blocks sink and some of the blocks floated. So here, density depends only on mass. So greater mass equals greater density, which means the object will sink. And smaller mass equals smaller density, so the object floats. As you can see, our 4 and 2 kilograms, they're lighter than 6 and 8, so they're floating. In the next experiment, we're gonna have same density. Here we can see that all blocks, the last one, they float, but we have here a very important part, that the object's density should be smaller than water's. In that case, only in that case, it will float. So here, we're gonna have, here we will increase the density, and we can see that all the blocks sink. That's it. My experiment number 3 is going to be about charges and fields. So first of all, let's see our main formulas. Here, it's electric field equal to KQ divided by R2. R is our distance, K is Coulomb's constant, and Q is charge, point charge. Here, for the first formula, let's see. We're gonna take a charge. For example, we're taking a positive charge. Oh, another thing that I want to explain is that when you put positive charge, it's gonna go out of the charge. And when we use negative, it's going inwards. So our positive charge, let's take one positive charge. And for example, here, let's see the electric field at this point is going to be 12 volt. And now when we come closer, it's going to increase. And when we come farther, it's going to decrease. So here we can see the dependency of our electric field on distance. So as distance grows, electric field decreases. Now let's put another point charge, but this time it's going to be negative. They're charged the same, but they just have different signs. One is positive, one is negative. So let's take our equipment to check the electric field. And we can see that using superposition principle, which the formula is right here, E total is equal to electric field 1 plus electric field 2. We see that if we measure in the middle, it's gonna be 0 here. It's very hard for me to find like the middle point here, but it's approximately somewhere here. Yeah, it's very hard to find it, but it's gonna be 0, and you can see it's almost in the middle. So here the electric fields will be equal to 0 because they're opposite to each other. So they cancel out each other, the positive and the negative one. So from this experiment, we can see that electric field strength depends on charges and distance, according to the formula that I showed in the beginning, and that electric field from multiple charges combined by the principle of superposition, we saw when our two fields canceled out and it was 0, and we saw how field patterns clearly show attraction, repulsion, and 0 field points. And that's it. Thank you for watching. Bye.